That's right, and thank you everybody for still being here. The workshop is nearing the end, but thanks for sticking with me. This is a 15-minute talk, of course, so it's going to be fairly dense. I think you'll find it worth to pay attention. So as the introduction already mentioned, this is work done at Silicon Valley, Blackstone Research Silicon Valley. I'm Dr. Mata, and we did this with my colleagues, Kids Bosbach and Michael Izar. So SPECTRE stands for Speculative Transactional Execution. And what this work is about is running new workloads on the cloud. Before, we wouldn't be able to run efficiently. But let me start at the beginning. So I probably don't need to convince you that today companies have to deal with a lot of data, and so you can't process it in just one computer. You're going to have to use a cluster of computers, or a cloud, as we say. And when you run things across more than one computer, you run into this very classical problem I have here on the slide you all already know, which is that if, for example, you have one guy adding 1 and somebody else adding 10, you expect to get 11 more at the end, but if you run these in parallel at the same time, with that box over here, you're not find the wrong answer. So we have to take care that parallelism works right. So for some workloads, it makes sense to plan conflict away. For example, you can have trivially parallelizable workloads where simply every computer works on different parts of the data. This is the easiest thing to do. Sometimes you can just stream different parts of the data through the system, and then computers take turn working on things. You have systems like MapReduce and DriveLink that work on this. This can be very efficient because you can read all the data large numbers at a time and ship them and pipeline things. So it's really nice. If you want to work at a lower level, you can use things like MPI, where you deal manually with sending messages, and you use, for example, barriers. So now you have to work carefully to make sure that there's no conflict in the way that you access the data. Now, sometimes, instead of spending all the time to carefully plan that there be no conflict in the data accesses, you can instead have the runtime detect them and deal with them at runtime. So you can do this using locks or transactions. And this allows you to do something different, namely distributed shared memory. So the idea here is that now, instead of streaming the data through your system, computers can read or write any part of the data. And the traditional distributed shared memory systems would be using locks. Now this is great on one hand because it allows you to do some things that would be some workloads would be really difficult to express as a data stream, that you can express them this way. But distributed shared memory as it stands has some challenges. I think some of the earlier talks mentioned the problem of latency on the network. So we have these two problems. Synchronization doesn't scale, and you have the problem of dealing with the remote read latency. So what do I mean by synchronization doesn't scale? What I mean is if you have a single lock, you will find that as you are working with a lot of data, you're going to have more and more conflicts. So one way out of this is to use transactions instead. And this is what we do in our SPECTRE system, Speculative Transactional Execution, as I mentioned at the beginning. So what we want to do is we want to take this distributed shared memory, but make it run faster and more efficiently to make it practical to use in the cluster. So instead of using locks, we're going to use transactions. So we're going to have everybody read and write whatever they want, and when they're done, we can compare the read and write sets, figure out if there was a conflict, and if there was none, we can speed ahead and win a lot of time. So we don't need to wait for the machines down. Other ways that we don't need to wait for remote machines is we're going to speculate on reads. So instead of waiting for the data from the remote machine, we'll just use whatever data we have at the local cache, and if this was correct, then we saved a lot of time. And suppose it was not correct, then when we get the answer back, we just start over. It's not bad because this is the time we would have started otherwise anyways. We can use the same trick of speculation to do other things. For example, we can, and I'll show you this later as well, we can actually also speculate past the commit point. So what this means is that when we write data, we can just speculate that there was no conflict and move forward. So the way you use a system like this is you break your computation into a number of transactions, what we call them tasks here in this talk, and then we're going to use software transactional memory to detect any misspeculation and then roll back when necessary. So using these speculation, these transactions instead of logs, work really well for some workloads. And this is the kind of workloads where speculation is going to succeed often. For example, you have a lot of data localities, so your cache is often correct, and you have a lot of opportunities for parallelism. So I'll give just one example on this talk for workload of this, and this is the newbie belief propagation. So what this looks like is you have some arbitrary graph, and here, here's some pseudo of what you're doing. Essentially, you're reading data from all of your neighbors, and then you update some value that is associated with your node. And here I have a big red node that's doing some computation, and if you look at it, you can see that you can do the computation on the big blue node at the same time, because none of them write something that the other one needs to read. So you could run some of these steps in parallel, and SPECTRE can actually detect this automatically using the speculation. And so the goal is that we get the same answer as if we had run this program in sequence, except we get the answer faster. So I want to emphasize that SPECTRE is a work in progress. We're not done yet. Our focus is to precisely describe the kind of workloads where speculation is most helpful. And because we have a focus, that means we have things that we're not focusing on. And these things are backwards compatibility. So we're not worried about having to rewrite our programs using SPECTRE. And the other thing is, for now, we're postponing making the syntax user-friendly, and we think we can do a good job in the future. So let's start to dive deep now. Here's what the SPECTRE API looks like. So it has two kinds of operations. The ones in blue at the top are ones that deal with accessing data. So you can allocate data, you can read it, you can write it. And then in red, remember I told you that you have to split your computation into the tasks. This is how you tell the system that you have tasks that are either sequential or parallel. So here in the example at the bottom, I have two tasks in sequence, and then these tasks B and C are in parallel. Now, in some systems, when you have tasks in parallel, you have to carefully make sure that they don't access the same parts of memory. In our system, this is not the case. So you can do whatever you want in B and C, and the system is going to figure out whether it can run these in parallel or not. So the guarantee that you get from SPECTRE is serializability. And what this means is that given any SPECTRE execution, there exists a serial execution consistent with a specified schedule that yields the same result. So in the example here, what this means is that if this is the program that you gave to the system, and obviously, I have dot here, you would have actual computation in there. The result after running this would be either the same thing that you would get by either running one by one in sequence, first main, then A, then B, and then C, or main, then A, then C, then B. You will get nothing else. So you don't need to worry about accessing this joint pieces of data. All you need to worry about is which orders are okay for you. So the way we build this, we have a traditional two-tier architecture. So we have a bunch of processes that are in charge of running the computation, and these are going to keep cache data of the previous values they have seen in the system. And then we have a storage tier whose processes are responsible for keeping track of the authoritative copy of each data item. And for a lot of workloads, it's actually possible to hold the data entirely in the memory of these machines, so we never have to wait for a disk, so we can go faster. We have written this in C#. This is an object-level collectible memory. And just to emphasize, so on these running nodes, we may keep several versions of the same object because we are speculating ahead of time. So these are the most important and perhaps also the most complicated slides in the talk. So here are two examples of the way we use speculation to reduce latency. So the first is speculate on reads. I mentioned this briefly before. So on the right, you have a program here. A traditional way of writing the program would be to try to read the data, wait until it's here, then run your computation and write the result back. What we're doing instead is we're going to use the data that we have seen the last time and run with it. So we start here immediately. We skip all this waiting. And we can send a read at the same time. And then eventually the system will come back